Okay, question 10. Figure 19 shows two objects, E and D. E emits a sound, so all the time this is making a sound. Let's imagine it's going bop like that. D detects the sound and E's moving away. So as you know, like an ambulance, if it moved away from you, you'd have if it started as neenor, 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 the waves get stretched. If something's coming towards you, the waves bunch together. So that's if I've got an ambulance again, neenor, 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 and it's going to get closer to you. So E emits a sound of wavelength 1.86 meters. D measures the wavelength as 1.98. Calculate the difference. Easy. Take the 2 away. So, done. The velocity of sound is 300 meters per second. Calculate the velocity of E. And it gives us an equation that you didn't need to know. It's just saying, can you read this equation and see what's going out? So we know E, the velocity of E, is the velocity of sound. Tells you that there. 330 times the difference in wavelength, which you worked up there, 0.12, all divided by the wavelength that E emits. 1.86, and you just put all of that together and you get 21.3. Next one, the wavelength of light emitted from distant galaxies is different when the light is detected. Explain how this differs. So this is the idea that galaxies are receding away from us. So here's us on Earth, and it's doing so at a faster and faster rate, and this stretches the waves. So we can imagine if this is emitting light like this over time, we get it more redshifted. And this is telling us that it's moving away. So we just got to put that into words. So the wavelength is increasing from distant galaxies. So it's been redshifted. And this shows us that galaxies are moving away from Earth. Now, sometimes they'll link this also to the idea that if I've got a galaxy, so let's say here's Earth, Galaxy A and Galaxy B, this one is even more redshifted, so has even longer wavelengths because it's moving faster away from us than this one. So they're both moving away, but this one's moving away super fast. There we go. Okay, cosmic background radiation provides evidence that the universe had a finite beginning. So this is the Big Bang. Use the table to give a typical value for the wavelength of CMB. So it's checking, do you know that the M stands for microwaves? Yes. Done. So cosmic background radiation. So there we go, 1.0 millimeters. During the evolution of star, the nebula collapses and becomes a main sequence star. State what causes the nebula to collapse. So that's gravity. So gravitational attraction or gravitational force. Explain why the nebula stops collapsing as it becomes a main sequence star. So it's this one that I've tried to teach you off by heart. So work is done by gravity to compress the dust and gas. Temperature goes up, pressure goes up. So temperature and pressure increase. Fusion takes place. And then the star is stable as the force of gravity inwards is equal to the gas pressure outwards. So if we quickly go through, I've got dust and gas. In one place there's slightly more. This does work by gravity, force times distance. Temperature of this goes up, pressure of this goes up. Now we get fusion. Eventually, the star will expand and it won't be very stable at the start. But then we have two forces on a main sequence star, gravity pulling inwards and the gas pressure outwards. And these will equal each other until it starts to run out of its fuel. And then it will start to burn larger and larger atoms. And for our sun, it's going to expand to a red giant and then collapse. That's it all done.